We're going to talk about density. So this is something we experience all the time, density of cars on a freeway. So in this picture, suppose the density of cars per mile is density, and that's equal to 1,000 e to the negative 0.01 x cubed cars per mile. Okay, and what is x? X is the number of miles forward from this picture. So this is like mile 0 that we're looking at. So how many cars per mile are there at the x equals 0 mile mark? Just right at that moment. And that would be like an actual exact moment, like right here, right across there. Okay, so we would have the density there would be this with the 0 plugged in, evaluate out, and you get 1,000 cars per mile. Okay, so at that snapshot, there's about 1,000 cars per mile. But this function is smooth, continuous, and it's decreasing because there's a negative sign here. So the cars per mile density is dropping smoothly every inch that you take forward on that freeway. How many cars per mile are there at the 1 mile mark down the freeway? Put the 1 in there. 1, about 990 cars. So the density of cars is decreasing. It went from 1,000 down to 990, and in fact it's decreasing every small part of a mile as you start from 0 and go forward. So the question is, how many total cars are there on the freeway from mile 0 to mile 5? So you draw this picture. Here's the freeway represented by this line, 0 to 5 miles. You pick an X location, and you say to yourself, how many cars are in this delta X segment of miles? Well, the delta X duration of mile is so small that the density is approximately constant on that small delta X interval. So at an exact X location on the freeway, there are this many cars per mile. And so in that delta X increment of miles, there are approximately this many cars per mile times delta X miles. So cars per mile times miles is going to give us total cars. See the miles cancel out. You just get cars. Always a good thing when the units cancel out right. So you're left with just cars. So naturally, all our calculus training says we're going to add up those chunks of cars as x, assume all its values from 0 to 5, add them all up, turns into this integral. Now it turns out that we can't do this with our little techniques. It can't be done in the usual closed form. So, but if you run Simpson, then we ran it with 100, I think. Turns out that in the 5-mile stretch total, there are about 3,865 cars. Okay, so now we're going to a different example. Here's the old rectangular sheet of metal that is 2 inches by 6 inches. Here it is. and it's manufactured so the density of the metal is equal to 5x grams per square inch at a location x inches from the left edge. So we're talking about at a location x, we're talking about the area of a delta x strip there being 5x grams per square inch. So what is the total mass of the strip of the sheet? A delta x strip of the sheet at an x location has mass 5x grams per square inch times 2 times delta x square inches. That's because it's too high and delta x thick. So that all works out to 10x delta x grams. And naturally then, because again, the square inches cancels off. Always a good thing. Then the total mass is this Riemann sum, turns into this integral, which evaluates out to 180 grams total for the whole sheet. So the sheet was real light, can I spell it that way? And then it was heavier or more mass over on this side. So heavier as you went this way. And then the whole thing added up to 180 grams.